In the previous lecture, we have been talking about the first moment of a plane area and its centroid. Continuing on that, in this lecture we define some more mathematical quantities and just work out some examples with them. The utility of defining such quantities would be clear later when you do rotational dynamics and so on. But in this lecture we are just going to restrict to their definition and working them out. So, the quantities I will be talking about would be 1, second moment of a plane area, two, transfer theorems. Transfer theorems, we mean how, if we know the second moment of a plane area in one particular set of axes, how do we transfer them to another set of axes. 3, we will be talking about relation between second moment and product of area. In particular, we will be focusing on how second moments and products of area, which we will define later in the lecture, change when we go from one set of axes to another set which are rotated with respect to the other. And then we will be talking about polar moment of an area. So, to begin with, let us define what is second moment and product of an area. And product. Suppose I am given an area, a plane area in xy plane like this. This is the x axis, this is the y axis. Then the second moment Ixx about the y axis is defined as, I take a small area, let me make it in blue, delta A, multiply this by the perpendicular distance from the x axis square. So, Ixx is defined as, take area delta A I, multiply by its perpendicular distance from the x axis and add it up. This is the second moment of this area with respect to the x axis, and this obviously goes to the integration y square dA. Similarly, Iyy, that is the second moment about the y axis, is defined as the distance of the area from the y axis is chosen, and then we write this as summation xi square delta A I, or in the limit of integration this becomes x square dA. These are just mathematical definitions. And then the product of this area is defined as integral x y dA, and I am going to call this I x y equals this. So, we have defined the second moment of a plane area and product of a plane area. Let us now work out some examples of how to calculate these. As the first example, I take a square of side A and calculate for it the moment of area about the x axis and about the y axis and its product of area. Ixx is equal to, by definition, y square dA. To calculate dA, I choose a strip at height y, because for this entire strip the moment of the area is going to be the same. So this becomes integral y square a dy, and y changes from minus a by 2 to a by 2, and therefore Ixx is going to be a times 1/3 y cubed minus a by 2 to a by 2, or this comes out to be a raised to 4 over 12. Similarly, to calculate Iyy, this is the square. I choose a strip like this and calculate Iyy as integral x square dA, which in this case would become integral, this is at distance x, so integral x square a dx from minus a by 2 to a by 2, and this also in this case by symmetry would come out to be a raised to 4 over 12. Third, for the product of area, you see that Ixy is equal to integral x y dA minus a by 2 to a by 2, and if I choose a small area dA here, this will be equal to integral minus a by 2 to a by 2 x dx integral minus a by 2 to a by 2 y dy. Antisymmetry of the function x and y, this goes to 0. So for a square of side A, Ixx equals Iyy equals a raised to 4 over 12, and Ixy equals 0. As a second example, let me take a rectangle of length A and width B, placed symmetrically about the origin. So this side is precisely a by 2, and so is this. It's not made to scale, but please understand this is a by 2 divided on both sides, and I want to calculate Ixx. For that, again I choose a strip here of width dy, because for this entire strip y square is the same, and calculate integral y square a dy is that small area dA, and y changes from minus b by 2 to b by 2, and this comes out to be a over 3 y cubed minus b by 2 to b by 2, or a b cubed over 12. Similarly, when I calculate Iyy, for that I choose a strip parallel to y axis and calculate integral x square dA, which now becomes x square b dx, x varying from minus a by 2 to a by 2, and this comes out to be a cubed b over 12. How about Ixy? Ixy, again you will see by symmetry, because the area is equally distributed on the negative side and the positive side of the y and x axis, comes out to be 0. So we have also calculated the second moment and product of area for a rectangle. As a third example, we will make it slightly more complicated, and I wish to calculate the second moment and product of area for an ellipse, a quarter of an ellipse here with semi-major axis A and semi-minor axis B. The equation for the ellipse is x square over a square plus y square over b square is equal to 1. To calculate I xx, which is integral y square dA, I choose a strip parallel to the x-axis of width dy and write this quantity as y square. The length of the strip, let's call it delta x dy. My job is to calculate delta x, and y varies from 0 to b. From the equation, x lower is 0, that is this point, and I also know from the equation of the ellipse that x is equal to a over b, square root of b square minus y square. Therefore, I x is going to be 0 to b a over b, y square is square root of b square minus y square dy. This is what we got to integrate. To do this, we substitute y equals b sine of theta. By doing so, I get I xx, which is a over b integral y square is square root of b square minus y square dy, 0 to b as a over b integral 0 to pi by 2, y square is b square sine square theta, b square minus y square square root is going to be b cosine theta, and dy is again b cosine theta d theta, and this gives me, this b cancels, and I get a b cubed integral sine square theta cosine square theta d theta 0 to pi by 2. This can be written as a b cubed divided by 4, 0 to pi by 2 sine square 2 theta d theta, which is a b cubed over 4 integral 0 to pi by 2 1 minus cosine 2 theta over 2 d theta. Doing this integral, when we do cosine 2 theta integral, that gives me 0, and the first integral is going to give me pi by 4, and therefore I get, for this shape where this is a, this is b, I x equals pi a b cubed over 16. Similarly, I can calculate I y, which is integral x square dA, where now I'm going to choose a strip parallel to the y-axis. The integral is very similar to what we just now did, and this will come out to be pi a cubed b over 16. How about Ixy? To calculate Ixy, I have to calculate the integral x y dA, where dA I take to be a small area at point x and y. And this can therefore be written as x dx y dy. X varies from 0 to a, and for any given x, a given x here, y varies from 0 to a y upper, where y upper is given by the equation x square by a square plus y square over b square equals 1, and that gives, for any given x, that y is going to be b over a square root of a square minus x square, and therefore Ixy for this is going to be integral x dx 0 to a integral 0 to b over a is square root of a square minus x square y dy, which is nothing but 1/2 0 to a x dx b square over a square times a square minus x square. This is a standard integral, so this gives me the answer a square b square divided by 8. Therefore, what we have determined is that for a quarter of an ellipse with semi-major axis A and semi-minor axis B, I xx is pi over 16 a b cubed, and I yy is pi over 16 a cubed b, and I xy is a square b square over 8. I'll now leave it for you as an easy exercise to calculate Ixx and Iyy, that is the second moment of an area with respect to x and y axis for the entire ellipse, and also show that Ixy for the entire ellipse is going to be 0 because of the symmetry between x and y axis. Using the second moment of area, we can also define something called the radii of gyration. By gyration, you can already see that these quantities are going to be useful when we describe rotation. The radius of gyration kx of an area A about the x-axis is defined through the relationship a kx square equals I xx equals integral y square dA, and radius of gyration for about the y-axis is defined as a ky square equals I yy equals integral x square dA. Thus, for example, when we look at a rectangle of length a and width b, we have already calculated that Ixx is equal to a b cubed over 12, and therefore kx square is going to be a b cubed over 12 ab, or equals b square over 12. Similarly, ky square is going to be a square over 12, and from these radii of gyration about the x-axis and the y-axis can be calculated.